There is a number that has driven the greatest minds of our species to the edge of madness. A number that appears in the equations of light, in the architecture of atoms, in the burning hearts of stars. It has no units, no dimensions, no explanation. And if it were different, just slightly different, by the width of a whisper, you would not exist. 0.0072935,256, or as the physicists prefer to whisper it, 1 over 137.035,999,206. This is the story of alpha, the fine structure constant. The magic number that Richard Feynman called one of the greatest damn mysteries of physics, and the question that Wolfgang Pauli, co-inventor of quantum mechanics, planned to ask the devil himself when he died. What is the meaning of the fine structure constant? Welcome to the rabbit hole. I promise to leave breadcrumbs. The anomaly. It's 1916. While the world tears itself apart in the trenches of World War I, a German physicist named Arnold Sommerfeld sits in his Munich office staring at spectral lines, those fingerprints of light that atoms emit when excited. Niels Bohr had recently given us the model of the atom, electrons orbiting nuclei like tiny planets. It was elegant. It was wrong. Because when Sommerfeld looked closely, really closely, at the light coming from hydrogen atoms, he saw something Bohr couldn't explain. The spectral lines weren't single lines at all. They were doublets, triplets, split like hairs. Sommerfeld realized that electrons don't just orbit, they relativistically orbit. They move fast enough that Einstein's relativity matters. They have spin. They have momentum in multiple dimensions. And buried in his mathematical corrections, emerging like a ghost from the equations, was a number. A pure number. No meters, no seconds, no kilograms, just 137. Now, here's your first breadcrumb. Dimensionless numbers are aliens in physics. Every other constant you know depends on human convention. The speed of light? That's 299,972,458 meters per second, only because some French guys in the 1790s decided how long a meter was. Change your units to miles per hour, and the number changes completely. But alpha? You could communicate alpha to an alien civilization in Andromeda without ever discussing units. They would measure it. They would get exactly the same number. It is a pure ratio, a cosmic password that works in any language, in any universe with the same physics. And that should be impossible. Because why should the speed of light, the charge of the electron, Planck's quantum of action, and the permittivity of free space combine to make exactly 1 over 137.035,999,206? Why not 1 over 42? Why not 1 over pi? Why not 1 over 666? Sommerfeld had discovered what Paul Dirac would later call the most fundamental unsolved problem of physics. The obsession. The 20th century belonged to physics. We split the atom. We built quantum mechanics. We conquered nuclear forces. And yet, this one number haunted everyone who mattered. Arthur Eddington, yes, the guy who proved Einstein right by photographing stars during an eclipse, became so obsessed with 137 that he tried to derive it from pure mathematics. He announced to the world that alpha was exactly 1 over 137, not approximately, exactly. He was wrong, of course, but the desperation in that wrongness tells you everything. Eddington believed 137 was the most important number in physics. He spent years constructing elaborate numerological proofs involving the number of protons in the universe. The physics community watched in fascinated horror as one of their greatest minds chased shadows. Then came Richard Feynman, bongo player, safecracker, Nobel laureate, genius. Feynman put alpha on his wall, literally. He stared at it every day. And in 1985, he finally committed his frustration to paper in his book QED, The Strange Theory of Light and Matter. There is a most profound and beautiful question associated with the observed coupling constant. It has been a mystery ever since it was discovered more than 50 years ago, and all good theoretical physicists put this number up on their wall and worry about it. Immediately, you'd like to know where this number for a coupling comes from. Is it related to pi, or perhaps to the base of natural logarithms? Nobody knows. It's one of the greatest damn mysteries of physics, a magic number that comes to us with no understanding by man. You might say the hand of God wrote that number, and we don't know how he pushed his pencil. Here's where we go deeper. Follow the breadcrumb. Feynman didn't just worry about alpha because it was mysterious. He worried because it is the coupling constant of quantum electrodynamics, QED. Every time an electron emits or absorbs a photon, the probability of that interaction is governed by alpha. Every Feynman diagram, those beautiful visualizations of particle interactions, carries a factor of alpha. When electrons dance, alpha calls the tune. And here's the thing that should make your skin prickle. QED is the most accurate theory in human history. We can calculate the electron's magnetic moment, how it spins, how it behaves in magnetic fields, using QED. We can carry those calculations to 13 loops of Feynman diagrams. We can predict values to 13 decimal places, and when we measure those values in laboratories, they match perfectly. We have achieved precision of parts per trillion. We can predict and measure with such accuracy that it's like measuring the distance from New York to Los Angeles and getting the width of a human hair correct. And we still don't know why alpha is 1/137. We can calculate with it. We cannot calculate it. The impossibility of existence. Now we descend deeper. Let me tell you about Fred Hoyle, 1957, Cambridge. Hoyle was trying to solve a puzzle that had nothing to do with alpha and everything with carbon. We are carbon-based life. Carbon is forged in the hearts of dying stars through the 3-alpha process, 3 helium nuclei smashing together. But the math didn't work. The reaction should have been too rare. There shouldn't be enough carbon in the universe for life. Unless there was a specific nuclear resonance, a particular energy level in carbon-12 nuclei that made the reaction probable. Hoyle predicted that resonance must exist. It was found. Carbon exists. We exist. But here's the breadcrumb most people miss. That resonance only works because of alpha. Hoyle and his colleagues calculated that if alpha were different by just 4%, not 40%, not 400%, but 4%, carbon and oxygen might never have formed in sufficient quantities. Stars would burn, elements would fuse, but the specific alchemy that builds biological chemistry would fail. Go the other direction, make alpha larger, say 130 instead of 137, electrons orbit closer to nuclei, atoms become smaller, chemical bonds strengthen. The electron in hydrogen orbits at 1/37th of the speed of light instead of 1/30th. Seems harmless? It's catastrophic. Electrons become too tightly bound. They can't hop between atoms. Chemistry as we know it dies. No molecules, no proteins, no DNA, no you. Make alpha smaller, 1/150. Electrons drift too far from nuclei. Atoms become unstable. The electromagnetic force weakens, stars burn differently, the universe goes dark and cold. Physicist Paul put it bluntly, if it had any other value, life as we know it would be impossible, and yet we have no idea where it comes from. We exist in a cosmic knife edge, balanced on 1/137, and we don't know who set the table. The running constant. Now, plot twist. I told you alpha is approximately 137, but I lied. Kind of. In 2020, physicists at the University of California, Berkeley, made the most precise measurement yet. Alpha equals 1/137.035999206, not 137, not
even exactly 1 divided by 137th. But here's the deeper truth, the one that will untether your understanding of constants. Alpha isn't constant. In the language of quantum field theory, alpha runs. It changes with energy. At the low energies of everyday life, room temperature, the temperature of the universe, it's roughly 1 divided by 137th. But near the Big Bang, at energies of 10 to the 15 Kelvin, alpha was closer to 1 divided by 127. The electromagnetic force was stronger in the early universe. Why? Because of virtual particles. The quantum vacuum isn't empty. It's a roiling sea of particle-antiparticle pairs popping in and out of existence. These virtual particles screen charges. At higher energies, you penetrate deeper through this screening. You see the bare charge. The force strengthens. We call it a constant because, for all practical purposes in our current universe, it might as well be. The variation over billions of years is minuscule, parts per 100,000. But the fact that it changes at all, that tells us something profound. Alpha is not fundamental. It is emergent. It is a snapshot of deeper physics we haven't found yet, like seeing the surface of an ocean and knowing there are depths below. Some physicists hunt for those depths in string theory, in extra dimensions, in multiverse cosmology, where every possible value of alpha exists in some bubble universe, and we simply inhabit the one where life is possible. Others look for variations in alpha across space, different values in different regions of the cosmos. So far, nothing conclusive, just that tantalizing 1967 paper by Pauli and Schmidt suggesting alpha might have been slightly different billions of years ago, or maybe not. The measurements are at the edge of possibility. The unfinished symphony. So where are we now? We have measured alpha to staggering precision, 137.035999200611. The uncertainty is in the last 2 digits. We have tested QED to limits that would make Sommerfeld weep with joy. We have built technologies, atomic clocks, quantum computers, MRI machines that depend on our understanding of this number. And we are still asking, why? In 2025, new papers claim geometric derivations of alpha from first principles. They sit in preprint servers, awaiting judgment. Some will be wrong. One might be right, or all might be wrong, and the answer lies in a direction we haven't conceived. Paul Dirac believed that fundamental constants must have mathematical explanations, that their apparent arbitrariness indicated incomplete theory. He spent his life searching. He died without finding. But here's your final breadcrumb, the one that leads out of the rabbit hole but points to another. The fine structure constant is not alone. There is the strong force coupling, the weak force mixing angle, the masses of fundamental particles, the cosmological constant, that infamous 10 to the minus 120 that drives physicists to drink. We live in a universe of numbers without explanations, constants without origins, and perhaps that is the deepest mystery of all, Not that alpha is 1 divided by 137th, but that we are conscious beings capable of noticing, of measuring, of worrying about it. Feynman's hand of God might be metaphor, or it might be the only language we have for a universe that appears fine-tuned for our existence, yet offers no user's manual. So, what do we do with a number that shouldn't exist, yet holds our existence together? We put it on our walls. We worry about it. We build cathedrals of mathematics trying to understand it. And sometimes, in the small hours of the morning, we wonder if the universe is asking us a question we haven't learned to formulate yet. The fine structure constant, 1 divided by 137.035999920611. A magic number, a cosmic password, a reminder that the most profound truths are not answers, but questions that refuse to die. Keep looking up and keep worrying about the numbers on your wall.